Hi there, welcome again to the Ivory Tower Collections. This video is going to be a little different than most of my others. It's not going to be really retro gaming focused. Instead, I am going to talk a little bit more about the newest and oldest tool I have here at the Ivory Tower Collections that I use for my console repair work and video game modifications that get sent to me. And that is this guy right here. I featured him briefly in another little teaser video. Oh, I don't know, it's been a couple of weeks ago. That was real short. But this is my BK Precision 1474 oscilloscope. And it's a very basic, very old oscilloscope. It dates from basically like the 70s and was discontinued by BK Precision, I believe in the early 80s or in the late 70s. I can't remember which. And again, it's just a very basic oscilloscope, but it's going to be perfect for my needs. So I thought I would show you a little bit more about this nice little guy. He's pretty cool. I'm new to oscilloscope use, actually, but have wanted to work with one and learn how to use one and have one as a tool for quite some time. But up until recently for me, I'd always thought they were very expensive and out of my price range. And it had never even occurred to me that they're fairly universal in their use, and for no more than what I do, I don't need anything crazy sophisticated. So I could pick one up and look for a used one for fairly cheap, and I did. I found this little guy, him and the cart that he sits on. He's on this little cart for 50 bucks on Craigslist here locally, and I felt that was a pretty good deal. It didn't work at first. I had to fix it. Had a broken capacitor inside, and when I found that broken capacitor, I decided I'd go ahead and replace all the capacitors. So that's been done. But anyway, so yeah, let's take a look at this nice little oscilloscope. Now, before I really turn it on, I'll show you a couple of basic things. It is a 2-channel oscilloscope. That means that it can I can use 2 test probes simultaneously to compare different waveforms on 2 different components at basically the same time. The scope does have the ability to view just 1 channel at a time, or I can view both channels simultaneously in what they call dual mode. And then it also has an option called add, which basically will add different values or voltage readings between the 2 different waveforms and kind of show me a new combined waveform appearance. So that's pretty cool. And now, all oscilloscopes have the same basic features. You'll have position knobs that allow you to adjust and change the shape and location of where the waveform is. They'll have these little grid lines across the screen that's called the gradicle, or at least older analog scopes like this always have these gradicles. It basically looks like a little scale. And in my particular case, on my scope, they're basically 1 centimeter by 1 centimeter, and it goes 10 across by 8 high. So basically it's an 8 by 10 gradical scale. Let's see, what else? Okay, well, all scopes allow you to pretty much change the amount of time you're viewing of your waveform. Waveforms occur in what they call cycles, and depending on how many cycles you're viewing or how much time you're viewing across the waveform, you can actually view multiple cycles. That's how you kind of see a common, what they call like a sine wave, which is a little curvy looking guy, or they got what's called square waves and triangles and sawtooth and a whole bunch of different waves. Anyway, changing the amount of time on the scope will adjust how much time you're viewing of that waveform, and likewise you can either view more or less cycles or just a single cycle if you synchronize it properly. You can also change the amount of voltage that you're reading between divisions or between these centimeter squares. So as an example right now, I have my channel B right here set to 0.5 volts per division. That means that each gradical mark is half a volt. So that means that every 2 gradicals would be equal to 1 volt of actual measurement. Okay, so enough fun talking there, right? Let's see what this thing looks like, right? Okay, well, let me turn it on. And have to give it a minute or two to warm up. There we go, there's my gradical line. Looks like I need to adjust it just a little bit, so let me do that. There we go. All right, so you can really start your waveform from pretty much anywhere you want on the screen. I mean, I'm just going to start this one basically in the dead center. But really, depending on how tall your waveform is, you might have to lower the initial position line, or your zero line as we might call it, so that you can read more of the scale if your waveform is taller, or if it's going negative and it goes below the zero line, then of course you might have to adjust it higher to read below it. But I'm going to start in the middle, and I'm going to use a probe here. This is for my channel 2 or channel B right here, and I'm going to attach it to my calibration test point right here. Now this calibration test point is basically a tiny signal generator that most scopes have built into them, that's strictly for testing the functionality of the scope and to test for the accuracy of the basic voltage readings between the gradical scales. So my particular scope here is going to be reading at 0.5 volts peak to peak. Peak to peak means the total amount of voltage from what they call the rise and fall of a waveform, or basically the top and bottom of a waveform. All right, so I've got my probe connected. I am in channel B, but we don't see anything on the screen yet. Well, that's because on my selection switch over here for channel B, I currently have it in ground, which means that I just want to see a 0. I basically have the probe grounded, so I'm not getting a signal reading. And so this is to use to mark where my 0 line needs to be. Now, if I throw it into DC, we're going to see something a little different. There we go. That is a basic square wave, and they call it a square wave because it's basically forming a box. Now you probably only see just 2 dashes, you know, one above the other. But if I were to increase the intensity a little bit and perhaps adjust my focus a little bit more fine, you might be able to see that there's actually lines vertically that connect those two sets of dashes. I'm going to turn my intensity down a little bit because I know that on the camera it gets quite a bit stronger. And again, my particular calibration test point is 0.5 volts peak to peak. Well, I actually have my volts per division or per square set to 0.5 volts. So that means that from the top, or from the bottom to the top of this would equal 1 square, 0.5 volts. Easy enough. Now the official measurement to really test this tells you to go to 0.1 volts per division. And when you move it down enough, you should actually be able to count 5 squares or 5 divisions between the rise and fall of the waveform. And in fact, if I do that, and if I turn up the power on my gradical so we can see the gradical scale, you'll see that there's 1, 2, 3, 4, and 5. So 0.5 volts. So that's reading properly. That's good. Now this, like I may have mentioned this before, the calibration is off in quite a few places on this, and one of these days I'll break it apart again and I will attempt to calibrate it, but it is not necessarily a task for the amateur, so I'll need to be careful when I go about that. It's at least reading accurately enough for me to see what I need to see and to really learn how to use it. So I haven't really broken into that too much. Okay, well this is cool, but again, you pretty much just see a couple of dashes. You know, what more can we do? Well, let me show you what changing the time does. If right now we're at 0.5 milliseconds per division, so that basically means that we are at half a millisecond per square across. And that would be about right, because this is supposed to, each one of these basically equals up to 1 to 0.5. Okay, well, let's make it a little smaller so it's a little easier to read it. I'll bring it up like that. And let's change how many we see. So if I change it from 0.5 to 0.2, well, now that means that each one of these squares is 0.2 milliseconds. So now we're occupying basically 2.5 across, and that'd be about right. And if I go to 0.1, we basically just see one waveform, or basically one cycle. And I know that because a cycle is basically the point from the rise and fall of a single waveform. That would be essentially one cycle, and that's what we're looking at here. And if I increase my intensity a bit and adjust my focus, you can probably see the, let me move it over a little bit. There, you can see the line that connects to that, and that is the drop off in the voltage from the rise of the waveform to the fall and then back again. In fact, you can see the point right there where it measures back up, that little dot. Okay, so that's my basic square waveform. I'll be right back, and I'll attach my probes up to something else to show you something a little better. Okay, so what I've done now is I've got the test probe from my second channel here actually attached to the audio output circuit on an Intellivision over here that I am working on. And the Intellivision basically generates a bunch of square wave signals. So when it's playing back music, you actually have multiple square waves executing all at once, and you can view that on an oscilloscope. So I actually have the oscilloscope connected, the Intellivision is turned on and ready to go, and yeah, so let me select some music here through an Intellivision. And let's see, what do we want to listen to? How about the two-part invention? That sounds. Oh, you know what? Let's do this. Let's listen to some Requiem Mass from Mozart. That ought to work. So here we go. And watch the scope here, and you'll see the waveforms across. It'll look similar to a spectrum analyzer, but not exactly the same because it's comprised of square waveforms. And if we want to see perhaps a little more of the signal, I can reduce the size like that a little bit. And then of course I can change the amount of time. And it's becoming more and more difficult to see the individual waveforms. But there we are. All right. So yeah, so obviously you could see that we were able to view that and see that taking place in real time, very similar to a spectrum analyzer perhaps that you've seen before. Only this one again was showing us the square waves that were coming off of the square wave generator for the audio on the Intellivision. So all right, I'll be right back and show you one other pretty cool thing. I now have the probe actually attached to the composite video input line on an Intellivision just as it goes into the RF modulator box and gets combined with the audio to eventually form the picture on your screen. So here's the interesting thing about that. A composite video signal is exactly what it sounds like. It's called composite because it actually has a combination of the red, green, and blue combined into one signal that's called essentially the color burst, and then it also has like a luminosity and also a synchronizing signal. All of that is combined into one output or into one line. And the interesting and cool thing about that is an oscilloscope can kind of show you that. Even an older oscilloscope like this has that capability. Watch what happens when I flip the switch here so we can view what I have on the screen. There we are. Doesn't look like much, but we're actually viewing several different waveforms all at once here. The one along the bottom here that's a little brighter is the synchronizing signal. Again, the synchronizing so that it knows that everything is lined up and properly the way it's supposed to look. And then these other ones that we have in between here are essentially our color burst signals, which again, you know, if you can read the different frequencies and kind of begin to isolate them where they're at on each chip, you can also almost break out individually which ones like red, green, blue, and as well as the luminosity. And the luminosity also has a highlight that will hit here, and you'll see these two little points that go bing, bing, like that. See that? It goes boom, boom. Now, what that is it's kind of hard to explain, but that's actually working in conjunction with what I actually see on the screen. But before I show you what we are looking at on the screen, let's zoom in on this a little bit. And as you'll recall, one of the ways that I can zoom in on a signal like this is to simply change my volts per division. Right now we are at 0.2 volts. So I'm now going to switch over to 0.1 volt, and we'll drop this down a little bit so we can look at things a little easier. And go to we're now at 50 millivolts. So at this point in time, we can barely even view this thing on the screen all at once. So I'm going to just drop it down here a little bit. And we'll have to increase the intensity a little bit because we're zoomed in on it. And I'll see if I can adjust our focus so we can see it a little clearer. Okay, like that. Well, I guess that's pretty, but you know, we still don't really see much. Well, that's because we're still looking at a lot of data all at once here. So what we need to do is to kind of view it in sections. And in this case, we're currently at 1 microsecond per division. So maybe if we were to actually drop this down again, and let me get my ground there. There we go. Lock it back in. Let's try changing the amount of time we're viewing and see if we can see a little bit more data. Now as I do this, it's going to throw the synchronization off a little bit, so I will have to adjust my triggering to compensate. Okay, so there we go. So we're currently looking at some of the signals right now. We're kind of looking at part of the color burst and the luminosity intensity on one spot. Now, there was actually a lot more than this. Remember, I'm kind of zoomed in. I'm just looking at a part of it. Well, the way that you do that is, let's change the time again. And there we go. Now, let's say I want to look at that part right there. What I can do is use my horizontal position knobs to adjust basically what I want to view roughly in the center of my screen or in the gradical. Again, I can turn on my gradical's luminosity so I can kind of view that. And then change the amount of time I'm viewing. So like that. So now we're looking at two different color burst options here. And if I continue to zoom in, I'll start to see even more detail in the signal. And I'll have to change my triggering. Ah, there we go. Perfect. Just about perfect. All right. So now we're really zoomed in on one of these signals. We're really looking at it pretty close here. And I can continue to go even closer if I can get my triggering to adjust. There we go. Now we're looking at another part of the signal. And I can get in even closer. And again, by changing what I view through my triggering, I'm actually changing what part of the waveform I currently want to view. And the way the trigger works is, imagine there's an imaginary line that when I adjust this trigger level, I'm moving this line up and down. And basically, by changing where this line falls, it essentially changes what I can currently view within the waveform. Now, the thing is, it's not perfect. I'm still going to see, you know, a composite or overlay of other waveforms behind it, but essentially I'm looking for the brightest parts, and that's the sections that you would look at in more detail. So there's a highlight there that we can see going across there. It actually is almost like a square wave that goes across there in the way that it appears. So yeah, that's pretty slick. Let's see, that's me looking at a lower frequency side of things. That's going to probably try to lock in, and that's okay. That's basically the same thing there. So yeah, that's essentially how the oscilloscope works and what it allows me to look at. So you know, just kind of a cool extra tool for me to have here at the Ivory Tower, which is very handy. And in case you're wondering what we're looking at, in reality, what's actually being shown on the screen, I'll see if I can adjust this, and it'll make sense what those little points are that you saw that are blinking at the top. So let me get my camera adjusted here. Actually, that intensity is even brighter than I thought it was. Okay. We are actually looking at the LTO flash screen. And let me see if I can adjust that brightness down. Well, no, guess not. Anyway, those peaks that you saw correlate with the highlights that go across the words LTO and flash. So that's actually the color white that flashes across there over those letters, and that is literally what we were viewing on the scope at the same time, which is really kind of cool. There, that's a little better. Okay, so yeah, now you can really see what I see here, and see the different signals, and you can see again those two little blips here and over here correlate to the flashing of the letters. So yeah, that is my BK 1474 30 megahertz 2-channel oscilloscope, and I've been having a lot of fun playing with it. It's going to be a great tool, I think, for helping me troubleshoot additional things. And yeah, so again, if if this kind of video isn't your cup of tea, hey, let me know. I realize it's not everyone's thing and it can be kind of confusing, but I've been having a lot of fun, just kind of like I said, learning a lot of this stuff, and had been wanting one of these for a while. So yeah, but don't worry, I've got some other videos down the pike or in the pipeline with some video games that I need to review and get showing. So there we are. Again, thanks for watching, and see you guys next time.